Hello, everybody. My name is Sanjay Pillai. I'm the Director of Product Management in OCI Compute. And I'm really happy to be here today to talk to you about how, with flexible, fast, and efficient compute, we enable you to run your workloads on OCI. Let's go through with our standard safe harbor statement. And then let's talk about what the three pillars that we want to kind of walk through today. So to enable you to run sort of your workloads your way, the first pillar is sort of flexible compute. This is the ability to match compute resources to your workload rather than the other way around, right? And then the second pillar we're going to talk about is best-in-class hardware that enables you to choose resources that give you the best price performance. And then finally, we want to talk about how not all workloads are built the same. There are some workloads with quite different application profiles, but we have features to enable you to run those efficiently on compute resources. So let's start with flexible compute, right? To discuss flexible compute, we first have to kind of set the context a little bit, right? So if you think about how people run their workloads on computers today, right? It starts with traditional on-prem workloads, where what you had to do was design and purchase hardware that was built not only to handle the highest peaks, but also needed additional buffers for as your workload changed, as the traffic changed, as your business changed. Now, as you can imagine, this is highly inefficient. And moving to the cloud obviously makes things a lot better because you're paying just for what you use. But in other clouds, you have to use fixed shapes. So while you don't have to essentially hold this hardware on your books for a long period of time, you still have to plan for certain peaks because moving to different shapes is hard. What OCI does with flexible shapes is enable you to tune these resources to your workload much more closely than you can with fixed resources. And what this gets you is a more efficient use of resources, which reduces your spend, which means more money that you can use to run your business. But where we want to go is a place where you can not only have flexible shapes, but these shapes can be auto-scaled both horizontally as well as vertically to match exactly your workload as it changes dynamically, right? This is the goal where we're going. This is where we believe the promise of the cloud will be met. So let's talk about flex shapes a little bit more. Why do we need flexible shapes? When we started to build flexible shapes, one of the things we realized is that that applications are very different. There are some applications that are CPU intensive. Think about this as streaming or certain compute intensive applications like AI ML or encryption. But then you have got applications that are memory intensive, like in-memory databases. You've got applications that may be quite balanced, like web servers, but whose usage will change over time, that are quite dynamic, right? And cost is always an issue, but for certain customers, like SaaS businesses, where this really affects the bottom line, these workloads are much more attuned to the resource usage and the budget that you're spending on it. So flexible shapes and compute in general have to be able to support those kind of different needs. And fixed shapes are not really designed for that, right? They are designed with certain optimal ratios in mind. The classic balanced ratio is about a core, 2 vCPUs to 8 gigs of memory. But if you need more than a core, then you have to go to 2 cores or 4 cores or 8, 16, 32. So it's a step function, right? And that is not, it's almost harkens back to a world where you got computers in certain shapes, in certain configurations, because that was better for the manufacturers. But in a cloud world, there's no reason why we have to be constrained to those. So if you need, let's say, 3 cores and 9 gigabytes of memory for a compute-intensive application like streaming, then why do you need to have to pay for 16 cores and all that extra amount of memory, or 8 cores and 64 gig? Whatever that shape is that you're trying to fit it into, you're always going to find some gaps in there. And at scale, that really matters, right? I mean, people often think of it as one VM, but when you look at some of our customers that are launching thousands and tens of thousands of VMs, that additional cost starts to add up. And this is where Flex really comes into the picture. With flexible shapes, you can choose the exact amount of cores and memory you need. And then when your workload changes, you can resize them when needed. Earlier in the Q&A, there was somebody who asked that exact question, that if they were had decided to go with 4 cores and 16 gig, but then realized they didn't need all of those 16 gigs, what would they have to do? And the answer is simple. You just change the amount of memory, restart your instance, and then you are using just what you need and paying just for what you need. But when we design flexible shapes, what we also realize the benefit of it is its simplicity, right? With fixed instances, what other clouds try to do to enable you to match to whatever your workload is, they give you a range of different fixed shapes. You have fixed shapes for general purpose, for compute optimized, for memory optimized, higher memory optimized shapes. It just goes on. What OCI does with flex shapes is you just have one shape, and then you choose exactly the number of cores you want, exactly the amount of memory you want in increments of 1. And that simplicity allows you to avoid the sort of cognitive overhead of trying to manage all of this and then wondering whether you have budgeted correctly, or whether you have been inefficient, and how do you try to save. It gets so much more simpler with flex shapes. But we beyond just the shape configuration itself, our pricing is also simple. Right. In a lot of in other clouds, to get a sort of a low price, you end up having to commit your resources for a long period of time, 1 year or 3 years. Now, that's great if you can predict what your workload is going to look like a year from now. But I suspect for most businesses, that's going to be pretty hard to do. So what you end up then doing is a constant game of trying to figure out, did you commit the right number of resources? Do you have to adjust the number of resources? Because when you break the bounds of what that commitment is, suddenly, and you're paying the list price, that price is significantly higher. On OCI, we start out with what we call our everyday low pricing. So if your business needs to change, you don't need to worry about sitting down and calculating how your commitments are going to work and whether you should adjust them or not. You just adjust the shape of the instance and you keep running your business, right? This is what Flex is designed to do, and this is how OCI Compute is built, is that we manage the resources. You run your business. And there's one more point I want to make on pricing. Businesses and enterprises are international, right? And we want our pricing simplicity to extend to that global reach as well. So all of our hardware shapes, all of our that you want to run your workloads on are available in all regions and at the same price. So now you no longer have to figure out whether if you're in the East Coast of the US versus the West Coast of the US versus somewhere in Japan versus somewhere in Brazil, what is the price you're going to have to pay? Is that going to adjust? Is it going to change? No, it's consistent, it's straightforward, it's the same price for a core, no matter where you are. And this ultimately is flexible compute. The ability to match the resources to your workload at a consistent, simple price, rather than to have to spend your effort trying to figure out how to match your workloads to compute resources. But no discussion of compute can be complete without talking about hardware. That's, of course, what we do at the end of the day, sell computers. And what we want to offer in OCI Compute is the freedom to choose with best-in-class computing. Because just as we talked about how workloads are different and you can tune the shapes to your workload, the same is true for hardware. We know that based on the workload, different hardware will perform differently. And rather than asking you to fit into particular hardware types, we want to give you that choice. We want to tell you that you have the ability to choose the latest and best hardware from AMD, from Ampere, Intel, or even specialized hardware like NVIDIA GPUs. And that's really what enables you to decide what is best for your workload. And all of these come in both bare metal form as well as in VMs, and in all of our regions. Let's talk about some of this hardware a little bit in detail. Starting with AMD. So on AMD, we offer our E4 standard compute instances that are based on the third generation AMD Milan processor with 2.55 gigahertz base frequency. This provides 15% better performance than the previous generation E3 standard based on AMD Rome at the same cost. And what the AMD instances enable is scale with 128 cores and 2 terabytes in a bare metal shape, but also with flexible VMs that go up to 64 cores and 1 terabyte on a single VM with our flexible shapes. And we have seen customers really start to adopt AMD hardware, and they see the value, the price performance it offers, and they're able to seamlessly move all of the x86 workloads onto AMD. The E4 is designed for a range of different applications and workloads. And one example of customers that have taken advantage of this is Phoenix. So Phoenix is a company that provides real-time streaming of things like sports events, online events. And what they have seen by using AMD hardware and by using our Flex instances is that they've been able to tune their compute exactly to the performance they want and at the scale they want, and save an estimated 40% going from fixed shapes to flex. And this is something that Phoenix has been pretty excited about and is continuing to grow based on these AMD shapes. But we also have new storage optimized compute instances coming on AMD soon. Storage optimized instances offer a very high amount of local NVMe SSD. So think of this as low latency and high IOPS for workloads such as databases, file services, and more. And the E4 Dense IO comes in both bare metal and VM form, and the bare metal has 128 cores, 2 terabytes, and 54.4 terabytes of NVMe. So compared to our prior generation Dense IO 2, this is significantly better CPU performance, significantly increased scale with more cores, more memory, and network as compared to it. And one of the customers that's in the process of leveraging this is Tim Brazil. Now, Tim Brazil is one of the first, I would say one of the first companies in Brazil that have moved 100% to the cloud. And part of the services they're using on OCI is our Oracle Cloud VMware services. And these new AMD E4 instances will enable customers like Tim to take advantage of even greater CPU or memory VM deployment options per SDCC host. So this is something that we are pretty excited about. So look for more information coming in the next few weeks. And then last year, we launched our Ampere A1 compute instances. Now, these are our first ARM-based processors, running at 3 gigahertz, sort of like a consistent frequency. These are single-threaded cores, right? And what the Ultra processor and the ARM architecture enables is with greater power efficiency, more predictable performance, near linear scale, it allows us to offer these at a cloud leading price, which is we think this is the first penny core in the cloud today that you can get with Ampere A1. And this comes in a bare metal form with 160 cores and 1 terabyte, but also with a flexible VMs up to 80 cores and 512 gigs of memory. And with the introduction of these ARM processors, we know that it's part of a larger shift as customers start to explore these ARM processors. And to make it easy for them, as well as developers building solutions on ARM, we are excited to also offer a very generous 4 cores and 24 gig as part of our always free offering on OCI. And then for customers and partners who need more than this or building larger applications, you can always go to our always free page, and there is a way for you to apply to an ARM accelerator program that gives you access to more resources so that to encourage developers to build on ARM in the cloud. And our Ampere A1 instances are designed for a range of workloads, not only for general purpose workloads, compute intensive and memory intensive workloads, but also unlocks a new range of workloads that are sort of ARM native workloads. So partnering with companies like Genymotion, you can now run Android workloads directly on our A1 instances in the cloud that enables you greater scale, greater efficiency. One example of one of our partners who have used ARM Accelerator is the University of Melbourne, right? They have been building an IoT framework called FogBus 2. And that they were able to test that IoT framework using A1 instances in OCI. And what they found was that they were able to run their workloads on A1 just out of the box very easily. And they found the A1 instances to be really performant and really quick for their IoT data workload testing. So this is something we're very excited to see what customers do with ARM in the cloud. So I think there's a lot more that we're going to hear about ARM in the coming months. And then let's talk about Intel. Intel is sort of like if you will, the standard among compute instances, obviously. And we offer both our standard as well as HPC compute instances. And our standard 3 instances are based on the latest generation Ice Lake processor with 60% better performance than the standard 2 instance at the same cost. And with this great performance, you not only get it as bare metal form with 64 cores and 1 terabyte of memory, but you also have flexible VMs that go up to 32 cores and 512 gig of memory. So now you can have flexible VMs on AMD, Ampere, and Intel, thus enabling you to choose the hardware that you need with the flexibility that we promise you. And of course, Intel is essentially designed to provide sort of like the best performance on x86 hardware for a range of different workloads, including AI and encryption optimizations that are built into the latest Ice Lake processor. An example of a customer that's leveraged our previous generation Intel instances was Zoom. And with Zoom, we were able to get them from testing to deployment in 9 hours, right? Zoom needed to scale significantly during the pandemic, and leveraging Intel instances on OCI was how they were able to scale volume up to 30 times and meet their traffic demands during the pandemic. And then I also want to touch upon our HPC compute instances. These are also built on Ice Lake processor, but have a higher base frequency and are designed to be clustered together using a low latency RDMA network, right? And so using the cluster of these optimized 3 bare metal servers with 36 cores, 512 gig, and 3.8 terabytes of local NVMe storage, you can run really massively parallel scientific and computationally intensive workloads like those run by Nissan for some of their simulation and modeling workloads in the automotive, as part of their automotive engineering department. And so then what you get with the optimized 3 instances is not only the bare metal, but you also have flexible VMs that go up to 18 core and 256 gig. So I walked through a range of different hardware types, but fundamentally, what all of these come down to is the fact that you have the ability to choose the hardware you want and pick one that meets the performance needs of your workload, whether you need higher frequency CPUs, whether you need larger VMs, or whether you need NVMe storage or RDMA networking, excuse me, all of that with the ability to size the VMs to the workload that you have. So we have talked about flexible shapes and we've talked about hardware, but there are workload profiles that are still quite different from what would be sort of like a traditional sort of on-demand workload. And we have features that are designed to enable you to efficiently use resources, even for these kind of workloads. One example of that is sort of low CPU workloads. So for things like dev environments, CI/CD pipelines, or microservices, what you end up having is workloads that are that use a small amount of CPU most of the time, and then once in a while have to spike up. So think of this in a build pipeline where it's idle most of the time, and then you suddenly have to run a quick build, and then it spikes up, runs for a few minutes, and then quiesces back down. Rather than trying to modify that workload and adjust it to a more sort of consistent usage, one of the things you can do is use a burstable instance. What burstable instances do is allow you to pay for just a fraction of the CPU while having the ability to burst to maximum CPU for short periods of time. So what you can do, and I'll demo this in a little bit, but what you can do is choose the number of CPUs just like you would on a normal Flex instance and the amount of memory. And then you choose a baseline utilization of either 1/8 or 12.5% or half of 50% of your total CPU. Now that baseline is guaranteed to that VM all the time. But when it needs to, the VM can automatically use all of the CPU. But if you attempt to burst for a long period of time, then what we do is we cap your usage back to the baseline to sort of ensure fairness for other VMs that are also trying to use the other burstable VMs that are also trying to use the CPU. So what you have is a VM that is tailor-made for the workload, but you pay just for that baseline CPU, right? So if you're choosing a baseline of 12.5%, then you're paying 1/8 of all the CPUs that you've chosen, even though you have the ability to burst above that for short periods of time. That's always what you're paying. No matter what you use, you're always paying that baseline fraction of the CPU. And so this makes the pricing simple. You're not trying to figure out how how to make this workload fit into a particular shape. You just choose this according to how your workload profile, the baseline according to your workload profile, and you pay just for the CPU usage. And then what the key point that I also want to emphasize here is that these burstable VMs don't require any orchestration or management, right? If you need to be able to use additional CPU, then the VM just gets to use that CPU. But what about, but you also have instances that need to run only for short periods of time, but don't need to run for much longer than that. So these workloads that don't need this constant, consistent on-demand capacity that are either short-lived, like a dev test workload, or are interruptible, like a batch job, where you run it for a period of time, and then if the resources are not there, it can easily pick up from where it left off. Those kind of workloads are best suited for our preemptible instances. So preemptible instances are instances that are running on our capacity that's otherwise idle. So think about it from a cloud perspective, where we have a bunch of capacity designed for on-demand usage. But as that usage changes, we have a certain amount of idle capacity. And now you get to take advantage of that. So with a preemptible VM, when you launch, it looks just like any other VM, has the same features, same performance, but it's launched on this idle or buffer capacity that we have. And we give this to you at a 50% discount over your contracted rate. But in return, what it is we reserve the right to preempt you with a short notice. So we'll notify you to tell you when we need that capacity back. And so you can save your workload state, and then we terminate your instance so that we can use this now for other on-demand capacity. So, if your workload is either short-lived, a few hours, or if it's designed to be interruptible, where you can save the state and resume from where you left off, then that's tailor-made for preemptible instances. And the pricing is simple, right? It's a 50% discount, and it's a consistent price. Regardless of the region, regardless of the time. So you don't have this variable pricing that you see on other spot instances on other clouds. And now preemptible instances are now supported on all our VM shapes. So now it makes it even easier for you to run your workloads with preemptible instances. And then I also want to talk to you a little bit about something that's coming soon that we're pretty excited about, called container instances. So today, when you're deploying containers, you have to manage the underlying VM if you want that isolation and the security. What container instances allow you to do is enable you to use or get the advantage and benefit of containers, which are lightweight, that should be easy to launch, easy to terminate. So it enables you to get all the advantage of containers without none of the overhead of actually managing the VMs. So now you don't have to worry about, are you using VMs effectively? Are you sizing VMs? You just launch the containers you want with the cores and memory you want. We manage everything else. You pay just for the container resources, so that significantly improves the efficiency. These containers are fast to start up. And then, of course, it's the billing also is much more simpler with container instances. So this is coming soon. So look for an announcement in the next few months talking more about container instances. But safe to say that we're really excited about what this is going to do for our cloud native customers. So I've talked about a few of these pillars. Now, what I want to try to do is demo a couple of these for you. So the first thing I want to do is show you how easy it is to launch a flexible VM. So with flexible VMs in the console, if you just try to create an instance, what you can do is, and I'm showing you also that you can choose either as an on-demand or as preemptible. But to change the shape, you can choose from the kind of AMD, Intel, or Ampere instances, and then just use the slider to adjust the number of cores in memory, right? And in this case, I've chosen 17 cores, and then I've chosen the amount of memory by changing the slider. You can use the entry box on the right to adjust this even more to the exact amount that you want, and then that's it. That's what we launch. In this case, I'm going to choose an SSH key just so I can log in and show the VM itself. But but that's all you need to do. And then one of the things that you will also see is that while this is provisioning, you can see the exact amount of cores and memory you've chosen, but also notice the network bandwidth, right? So in our flexible VMs, the network bandwidth is tied to the OCPUs at 1 Gbps per OCPU. It goes up to a maximum of 40 Gbps on our AMD and Ampere instances and 32 on our Intel standard instances. Goes higher on our optimized 3 VM instances. So now that the VM is running, I want to be able to SSH and show it. So remember, you had chosen 17 cores and 152 gigs of memory. So once you SSH into it, I'm going to try to show with what the CPU and the memory is. So with if you list the amount of CPU or cores on the VM, what you will see is that it's got 34 vCPU or 17 OCPU in this VM, right? So if you see, it goes all the way from 0 to 33 in terms of processors. It's all on the AMD EPYC Milan processor, so you can see exactly this is what the VM has. And then if you look at the memory, then you can see also exactly the amount of memory that it's got. And so that's, it says it's in kilobytes, but when you convert into gigabytes, you'll see that it's got approximately 152. So I'm going to skip past this, and let's see if we can. The next demo I want to show you is burstable VMs. So with burstable VMs, what I'm going to try to show today is how we essentially manage the baseline and how that looks when your application is running within the VM. So what I'm doing right now is I am launching a burstable VM, but I've already launched a second burstable VM that I have been running for a while, and I'm going to try to compare how these two perform. So in this case, I'm choosing a pre-created volume because it has Sysbench and Stress and some tools that I want to use to demo this capability. So I'm choosing one core, 12.5% baseline. It defaults memory to 2 gig, but you can change and adjust this to the amount of memory that you need, and then you can launch the instance. So while this is going on, I want to talk a little bit about burstable instances. Like I said before, the burstable instances really enable you to choose the baseline CPU, but once it's set, you don't then have to worry about scaling or adjusting the amount of CPU, right? It's your application sitting in the VM will be able to use as much CPU as it can, and when we enforce a fairness because you have burst too long, then we'll just cap the CPU that the application can use, and there's nothing that you have to either build into your application logic or do any additional orchestration to manage the VM. So in this case, we're launching that one OCPU 5 gig with a 12.5% baseline. And then what we're going to do is I'm going to forward a little bit through this demo in the interest of time. And what I have is I'm showing that I've got another demo, another burstable VM that I had already launched ahead of time. So now what I'm going to do is I'm going to SSH into those two VMs, the one I've created just now, as the one I created before. And then in this, I'm going to fast forward through this one, sorry. So in this demo, I'm essentially, so when I SSH into the instance that I just created, you can see that it's got one core or two vCPUs in the VM. But what you want to show is that while that's the maximum amount of CPU, you want to show how much you can use, right? So what I'm going to do is I'm going to run sysbench on this new instance as well as on an existing instance that I have that's running. So I'm going to jump ahead a little bit. Okay, so what I'm showing right now is this is an instance that I've already been running for a while. And as you can notice that I've been running stress on this VM. And so you can see that it's a large number of its CPU usage is part of steal time, and the end of this called ST. Whereas it's the user time, which is the stress application, is only able to get about 12.5%, which is the baseline that is gotten. And the reason why is because I've been running stress for hours on it. And so what it's doing is after it's run for as much as it's possible, then the hypervisor or the underlying hypervisor will hold back the rest of this with steal time and cap the usage just to 12.5%, right? So what I can do is I'm going to exit, kill the stress on this one. So I've got this VM that's running essentially, that's been maxed out in terms of burst, and then I've got a new VM that I have not actually burst on. And so if you run a sysbench on both, what you can easily see is that it's got where the instance that's not been, that we just launched, you can get 240 events per second. Essentially, it's sort of searching for prime numbers. It's a CPU stress test. And so you can see how many events it's run. But on this other burstable VM, which I've been stressing out and essentially capping, ensuring that you cannot use more than 12.5%, when you run sysbench, you will see that it's got a significantly lower number of events per second, essentially showing that the application just wasn't able to use more than what the baseline CPU was. But when you can burst, then you can use all the CPU, and then you can get the full performance. So that's the benefit of using burstable VMs, is the ability to get the usage you want without having to essentially code for it. So I'm going to pause this demo and then go to the next one. And this, I'm going to go through this a bit quickly. This is a real-time inferencing demo. And what I'm showing here is the benefit of using Ampere A1 with for AI inferencing. So in this case, we're using a live feed from a camera, streaming it into a VM in the cloud, running inference using a pre-trained model to recognize cars coming through an intersection. So the key aspect here is that this is a real-time workload where the latency is very important. How quickly you sort of recognize the cars is very important. And in this demo, what Victor from Ampere Computing is doing is he is running the same model simultaneously on 3 different VMs. One is an Ampere A1 VM, one is an x86 VM from AWS, and then another one with a Graviton ARM-based VM from AWS. And in all of these, you can see he's streaming that camera from the intersection, and you can see the latency that in 30 or so milliseconds, it's recognizing cars. Now, all of these are able to recognize these objects in real time, but the optimizations that Ampere has built into deep learning software that you can run on top of the Ampere instances enables you to use their hardware more efficiently. So I'm going to skip out of this demo and talk about the next section, which is the cost comparison. And here's where the Ampere A1 instances really shine, is that with Flex and with the sort of low pricing of Ampere A1, you're able to run the same workload much cheaper on an Ampere instance as compared to either an x86 or a Graviton instance from AWS. And so we really would like to invite you to try out our Ampere instances when using our free tier. And so I'd like to wrap this up now by talking about how you can take the next step with compute with us. So we've talked about flexible shapes, how you can essentially match the resources to your workload, how you can get the best price performance with the latest generation hardware, and then how you can use compute features to tailor resources to your workload profile. Come check us out on the Cloud Compute webpage. We have got pre-built tutorials, architecture, reference architectures that you can look at. And then you can sign up at oracle.com, whack cloud, whack free, to use our always free AMD and Ampere compute resources, as well as a host of other resources that are available always free. Thank you so much for your time. It's really been exciting to talk to you about what we have done in OCI Compute today. We'd love to hear from you, and thank you again.